Hi, everybody. I'm Michael, just repeating what I said earlier. I recently graduated PhD from Berkeley Skylab, and today I'll be presenting on Agentix, a general LLM serving system for LLM agents as general programs. Ever since ChatGPT came out, the AI ecosystem has been evolving pretty rapidly. In late 2023 and early 2024, it was predominantly OpenAI and ChatGPT. Fast forward to now, and the AI ecosystem has vastly expanded into general agent applications. On the application side, there are countless examples beyond just chatbots, such as Claude Code, Cursor, Cognition, Replit, Lovable, Harvey, Perplexity, and etc. But from all these examples, it is abundantly clear that the application layer is growing exponentially and expanding into many different verticals and domains. Below the agent application layer exists the LLM serving layer. This includes model providers such as Anthropic and Google, and other neo-clouds such as Fireworks and Base 10. More importantly, the agent application layer and the underlying LLM serving layer are completely decoupled. For example, Claude Code runs on your laptop or your server, while the serving runs remotely from the cloud or a model provider. Diving deeper, the LLM serving layer consists of the LLM engine, such as VLM or SGLang, which manages an LLM's KV cache and schedules different LLM requests. An LLM serving system can horizontally scale across multiple engines or replicas for fancy techniques such as prefill decode disaggregation. And finally, a global load balancer, such as Kubernetes, can route requests to these engines and load balance these requests. On the other hand, developers or even application builders build their agentic programs via a general programming framework or language. Typically, in an agentic program, it consists of one or more LLM agents, defined as a tuple of a system prompt and the corresponding large language model. These LLM agents interface with the serving layer to get output tokens. All these agents operate over a global history, such as a cumulative conversation state, like in chatbots, or other more complicated ways to manage memory, such as paging. Like in Claude Code, these agents can perform tool calls with specific function or API calls and also interact with humans. By interacting with tool calls, agents can effectively manipulate external environments. This can range from surfing the web and manipulating robot arms to Claude Code such as executing terminal and modifying code bases. Finally, the red box, which is the orchestration layer, manages to control flow between all above components. Popular orchestration frameworks such as LangChain, LangGraph, AutoGen, and OpenAI Swarm. But at the end, we believe that general programming is a winning approach to expressing your agents. Now we will give examples of agent programs. The obvious trend we notice here is that agents are becoming increasingly complex. The most simple and original example is a chatbot, which alternates between large language model calls and the human. Going back to before, the higher level application or program is getting more complicated. Today, programs leverage the React paradigm, where an agent alternates between tool execution and the model. However, this complexity is only growing. For example, Claude Code today can launch multiple sub-agents, summarize the sub-agent results, and continue doing so until it terminates. Finally, the most complicated example as of today is Monte Carlo tree search, typically to search and discover novel algorithms, proteins, or materials. You can see that there's a lot of parallel calls and tool calls, and it is up for the program or the search algorithm to decide when different threads fork and merge with each other. Fundamentally, all agent programs exhibit three properties. First, programs are highly dynamic. It is unclear how long the program will run or when it will end. The second part is that programs can be fully distributed, meaning that there are multiple calls or sub-agents running in parallel. Finally, programs are highly non-deterministic. Even with the same prompt and the same seed, the execution pattern of the program can be very different. Given the sheer complexity and the dynamic nature of such programs, this begs the question, how can I efficiently serve these programs via my LLM serving engine? To that end, we introduced Agentix, an LLM serving engine that serves these complicated agent programs or large language model calls, not large language model calls, as first-class citizens. Here, programs similar to a Claude Code session are a higher level abstraction than a singular large language model call. Existing LLM engines treat each large language model call individually and optimizes metrics for these calls, such as token throughput, time to first token, inter-token latency, 95th, 99th percentile as SOOs. But this is largely ignorant of the bigger picture, which is how these calls are used in a broader application or program setting. Agentix instead enables stateful LLM serving. It optimizes program-level metrics such as the throughput of programs and program job completion time. It leverages statistics across language model calls in the same program in order to perform better resource management. With the LLM serving system being aware of program-level statistics, it essentially couples the agentic program and the LLM serving layer together. While the execution of the agentic program still happens on your local computer, the LLM serving engine is aware of which program the large language model calls come from. Thereby, it can leverage this information to optimize performance. Agentix can be roughly split into 4 sections. The first section describes Agentix front end. When a user runs an agentic program, it submits large language model calls over time, determined by the program's execution or control flow. Typically, the program calls the LLM via an OpenAI chat completions or completions endpoint. The Agentix front-end package then intercepts these LLM calls and annotates the OpenAI request metadata with the program ID and the thread ID, should there be parallel calls. This enables generalization to any program that calls into our engine. Users can leverage LangGraph, AutoGen, LangChain, or whatever framework they use. But in reality, standard Python or TypeScript programs are sufficient, as most of these frameworks are merely better abstraction layers. After large language model calls are submitted with metadata from the front end, Agentix backend populates a process table. More concretely, the process table is akin to the traditional operating system concept that matches the program ID to program-level metadata. This includes the total queuing time of a program across its calls on the LLM engine, the total runtime of the program, the engine ID of the program for the sake of the KV cache data locality, and the number of parallel LLM calls for distributed programs, and vice versa. All these statistics are basically leveraged to improve different components of the serving engine. With the process table caching program-level statistics, the Agentix higher-level load balancer across the LLM serving engines caused the process table to improve the prefix cache hit rate. We motivate our load balancer policy with 2 algorithms. First, LLM calls in the same program obviously have high prefix cache hit rates due to similar system prompts or cumulative context. Second, LLM calls across different programs have low prefix cache hit rates, but there's a small caveat here. Short LLM calls still have high prefix cache hit rates. This means that it doesn't matter where short large language model requests go. They are load balanced onto the least utilized engine. Long requests, on the other hand, can significantly benefit from being scheduled on the same engine as their corresponding program, preventing significant KV cache recomputation. Hence, Agentix schedules long requests based on the program's data locality. In other words, the engine where prior calls were scheduled on. This simple scheduling policy exhibits similar performance as Preble, which builds complex prefix trees on the load balancing layer and matches based on the engine with the longest prefix cache match. Finally, the scheduler leverages the process time, or the program ID, to better prioritize and preempt large language model calls. We identified two problems with VLM's existing scheduler, which follows a first-come, first-served policy, or FCFS. Due to FCFS, there exists head-of-line blocking at both the LLM call level, inspired by fastserve, and at the program level. For large language model calls, short LLM calls with short decode steps are delayed by long LLM calls with long decode steps, as identified in fastserve. We show this empirically over different program workloads, where short LLM calls with short decode steps suffer from a high ratio of waiting over actual runtime in the blue curve, meaning that short LLM requests wait too long with respect to how long they run. A similar problem can be found at the level of programs. Short programs with a small number of LLM calls also suffer from a high waiting over execution ratio, meaning that short programs are also waiting too long relative to how much they actually execute on the engine. To address these two problems, the agentic scheduler proposes two simple solutions. First, to mitigate headline blocking at the LLM call level, Agentix introduces the notion of preemption to LLM serving. Typically in VLM or SGLang, an LLM call is continuously scheduled on an engine until it finishes decoding. However, for programs, this is generally unacceptable since this behavior can lead to thrashing, where different programs keep blocking each other from finishing. Hence, inspired from traditional operating system concepts, we leverage a simple MLFQ or multi-level feedback queue as a core preemptive scheduling algorithm. This mitigates head-of-the-line blocking so that long LLM calls do not block short LLM calls. The real magic really comes from the priority function, which depends on program-level statistics. In particular, Agentix seeks to emulate shortest job first, an optimal scheduling policy in single-server scenarios. However, Agentix assumes no prior knowledge of program runtimes, and instead uses a process table to track a program's cumulative execution time on the LLM engine. By doing so, it approximates a least attained service policy at the program level. A program's first LLM call is placed at the highest priority, while over time, later calls in the same program are assigned lower priority since the program is older. Extending this to multi-threaded or distributed programs, Agentix gang scheduled LLM calls in the same program together, assigning them the same priority. Second, LLM calls in the same program are assigned priority based on the program's longest critical path, or the longest running thread seen thus far. Together, this ensures that super long 1 million context Claude Code sessions do not block shorter user sessions. This pretty much completes the description of the Agentix system. Finally, we discussed the evaluation for Agentix. We perform evaluation over 4 workloads, ranging from chatbot agent, which uses shared GPT, to React, which uses BFCO-v3 from the Gorilla project, and Monte Carlo tree search over the web shop dataset. Our final workload mixes all 3 workloads together to form this highly heterogeneous workload. Note that our MCTS workload is very resource intensive, as the average MCTS program consists of 160 LLM calls. Our single engine results show that Agentix can attain 4 to 15x higher throughput, program throughput, from programs than vanilla VLM given the same SOO latency, or seconds per token. These graphs show that latency, or seconds per token, over the x-axis, which measures the arriving programs per second. Our results stand out most in the mixed workload scenario, which is the most realistic setting. Across multiple engines, while keeping the scheduling policy constant on the single engine layer, being aware of a program's KV cache data locality can improve throughput by 1.4x on average and 2x for tail latencies for programs, indicated by the 95th and 99th percentile latencies. Notably, the performance of the Agentix load balancer policy is similar to Preble. For the offline setting, Agentix can reduce the make span, or time for all LLM requests to finish, by up to 40%. For more experiments, see our paper. Overall, Agentix is a serving engine for dynamic and general agent programs. Agentix makes no prior assumption of programs' workloads. Its scheduler and load balancer are non-clairvoyant, meaning that it just works out of the box. Our results are relatively impressive and can achieve over 10x performance for programs over the default VLM package. Thank you for listening to my speech, and happy to answer questions.